All right. Good afternoon, Rotary Club of Flint. All right, nice to see you all here today. Folks on Zoom, can you hear me okay? All right, we got the thumbs up. Today is Friday, February the 20th, not February the 20th. That's that. January the 20th, the other month. And today is National Cheese Lovers Day. So lasagna there with the cheese. Some of us might say that every day is Cheese Lovers Day. Also, Take a Walk Outdoors Day, Camcorder Day. So Rob, Jewel, you're all set. You got your camcorder now.
Oh, I should have brought it.
And it's also Penguin Awareness Day. So if you didn't know, a group of penguins in the water is called a raft. And very appropriately, a group of penguins on land is called, anybody know? A waddle. Yeah. So we have Lunar New Year that's going to be starting over the weekend here, which of course is the start of a new year as celebrated in a good portion of the world, including much of China and East Asia. And it's going to culminate on February 5th with a lantern festival. So it's for anybody who's celebrating that, hope it's a wonderful new year. And of course, if you are somebody who is fascinated by the stars, then today is the program for you. We're going to be welcoming Todd Flisher as well as Pat Ross from Sloan Longway. So let's proceed first with the Pledge of Allegiance. I pledge allegiance to the flag of the United States of America, which stands one nation under God, indivisible, with liberty and justice for all. And if you'll repeat with me the four-way test of the things we think, say, and do. Is it the truth? Will it goodwill of better friendships? Will it establish without concern? And happy to have with us today Julian Paczynski, who will offer our inspirational message.
Good afternoon, fellow Rotarians. Honestly, it has been a long time since I've been here, but that's the way life goes sometimes. Try to have a birthday because then Ellen always calls me and that's the last prompt I needed. There's a scripture that I have used in my life a lot, probably because I needed it more than maybe most. It's been a convicting scripture for the most part, but it's also an encouraging one. And it comes from Galatians chapter 5, verse 21, 22. And it basically says, the fruit of the Spirit are love, joy, peace, patience, kindness, generosity. I'm going to write self-control, joy, peace, patience, kindness, generosity. And the last two escape me, but it's okay. Yep, yeah. Caused no doubt by lots going on in our life. My husband and I sold our house, bought a house, did it all in 2 months and moved everything. An exhausting process, and did it over Christmas. At any rate, one of those fruit is kindness. And I thought, given our four-way test, it's a great one to focus on. I didn't want to pick patience because I'm not patient, but kindness, I think, is something we can all do. And we perhaps could do it more than we often think about it. And last night, Tom and I had an experience that prompted me to think about it again and to share this with you. We were late coming home from a grandson's basketball game. We stopped at the Grand Blanc Cottage Inn, pick up a pizza, so I didn't have to cook. And as I was getting back into the driver's side of the car, my husband, who has speech aphasia, hollering at me, no, stop, stop, stop. A gentleman had gotten out of his truck, collapsed, fallen onto the cement. I couldn't see him, but Tom could. And I began to witness kindness from any number of people. Now, I could tell you what their race was because it was a diverse group. I could tell you what their ages were because it was a diverse group. There were young people who came out of that cottage inn that worked there. There were bystanders who stopped to see what in heaven's name was going on. This poor man, Mike was his name, is bleeding on the ground. And of course, no one wanted to move him because didn't know how serious it was. And he had a huge gash in his head. But what I saw was the caring concern. The manager of the Pizza Hut, let's give him credit, Cottage Inn, came out, sat down on the cement. It was wet, it was rainy, it was snowy. He's laying flat on his back. I didn't have a blanket in the car. I couldn't believe it. I carried blankets in our car all the time, had nothing, but I found this one kind of a thing I could put under his head. A woman stopped and came running over with a coat and a blanket and just started wrapping it around him. And there was blood everywhere. They were calling 911. But here we sat. There must have been 7 or 8 people surrounding him, not trying to be too close or anything. Each person in their own way, uttering encouraging words or doing encouraging things. When the police finally came, and then some healthcare professionals who knew what they were doing, because they certainly didn't want me doing anything nursing wise, I was able to leave. And then it dawned on me that that's another point to kindness. We don't have to know what the end result was. I did what I told him I'd do. I said, Mike, I'm going to pray for you, and so will my husband, and we will pray that you will be completely healed and that everybody's going to get you back to normal. But each of us can help in different ways, and we don't have to know the end results. So that prompted me. See this book that's falling apart? My children tell me all the time, you know, Mom, you could tape that together. It happens to be an act of kindness that we receive. And believe it or not, Tom had his stroke in 2008. Jerry Ragsdale, many of you may know Jerry, came to the hospital, brought Tom this book called Grace for a Moment by Max Lucado. I don't think Jerry would believe or ever expected that when he gave Tom his devotional book, that's one day a year, that we would have shared it year after year after year, done a little history, note-taking, what was going on in our life, shared it with our grandchildren to the point where our grandchildren know if you go to grandma and grandpa's, you're going to have your devotional in the morning, and some of you are going to have to read and do. It's the way kindness stretches and unfolds and embraces others. So it just happened that 2 days ago, the devotional was this, and it's my final words, I'm sharing it with you. Sowing seeds, and it says sowing seeds of peace, but it could equally say sowing seeds of kindness. Want to see a miracle? Plant a word of love, heart deep in a person's life. Nurture it with a smile and a prayer and watch what happens. An employee gets a compliment. A wife receives a bouquet of flowers. A cake is baked and carried next door. A widow is hugged. A gas station attendant is honored. A preacher is praised. Sowing seeds of peace and kindness is like sowing beans. You don't know why it works. You just know it does. Seeds are planted and topsoils of hurt are shoved away. Don't forget the principle. Never underestimate the power of seeds of kindness. My prayer for all of you and for myself would be that others would see kindness demonstrated in our lives when they needed it most. Thank you all.
Amen.
Thank you. Inspiring words to each side, so please enjoy your lunch and we'll be back to the program shortly. Welcome back, everybody. You're welcome, of course, to continue eating, but we have a full program today, so I want to go ahead and get us started here. So to start with, we have a very special presentation here, the courtesy of Gene Dennis and his team of folks that have been helping to what would be the right archival term, to accession the items in the Rotary storage at SCAP, and to cull some things and to dig out some special treasures. So I'd like to invite up Gene so that he can share with us some of those special treasures that he's unearthed.
I've been fortunate enough to coordinate a team of Rotary pickers. That's like the American Pickers, if you've ever seen the TV show. We're Rotary pickers. I'd like to invite them up, Vic George and Mike Chafee. Come on up here with me if you would, please. We've been charged by the board of directors to pick through Rotary archives that are over at SCAF's warehouse and have been for a decade or so. And SCAF has finally said, hey, we want to get rid of this stuff. We got rid of Dave Smith. So, yeah, that's right. So in turn, they said, we gotta get rid of stuff, junk, whatever. So we've been sifting through it, Mike Chafee and Vic George and I in the last couple of Tuesdays, looking for real charms and real antique things that really belong to you, the members of Flint Rotary. And this past week, we came across something that was exceptional find. The exceptional find was a box full of glasses. And the glasses were shot glasses, wine glasses, and champagne glasses. Embroidered or named and engraved on the sides of them. 50th anniversary of Flint Rotary, 60th anniversary of Flint Rotary, and the 70th anniversary of Flint Rotary. Quite historic finds, and obviously they're leftovers from those that were held and were ordered for those things. We're here today to see if there are some members of Flint Rotary that would love to turn around and take something small. Fact is, Vic, show them the printer set that we've got right there. We got a 50th, a 60th, and a 70th. Wine glass, champagne glass, and I don't know, it's an awfully big shot glass. I guess back there, 1966, they used to make a little heavier. Anyway, we're wondering, is anybody interested in making a contribution to Rotary Foundation, Flint Rotary Charitable Foundation for that set of 3 glasses? How much?
I'll give you $100.
$100 sold. Yeah, take a. No, I hate to tell you this, but we've got one more set exactly. There's only 2, but we got one more set exactly like that.
I'll give $100.
I've got $100. I'm going to see if anybody wants to bid up $100. Okay, Mike Chafee gets the second one for $100. And now I think we've got a set of 2. A set of 2, it would be a 60th and a 70th anniversary. We got 3 sets. No, we got 2 sets of 2s and then this. All right, so we got a set of 60th anniversary and 70th anniversary, just 2 glasses. Is anybody interested in that set? $50. $50. Anybody want to do better than 50?
60.
You want 60? 50. I think we sold this one for 50. We got one more set exactly like it. Was that you, Mr. Jewell?
Oh, I would.
You said 60.
Oh.
Is that a firm bid or was that a? Yeah. It's a 60 and a 7. All right, $50, $60.
I'll thank you for.
$50. Okay. Notice how he talked himself out of that. Does that surprise you? Not at all.
Oh, you got the camera.
Now we've got a matching set. It's 2 glasses, both of them 70th anniversary. They would be 70th anniversary. What year? What year? 1986, right. 1986, two 1986 vintage.
Cheater. He had it on the glass.
70th anniversary. Would somebody like to take home and be the proud owner of them? Yes. $50? $50 it is. We've sold. Good. We've
Good deal.
taken care of that business. Now we've got one other thing that we'd like to do. Yeah. Rita, would you come up here? One last item that we found that we thought was a real find, and this one we aren't going to ask any payment for. Mike, tell her what we've got here.
The, as you, that they've been around for a long time, know that it used to be a tradition in Rotary to trade banners with the visiting club. Well, we found not a banner, but a medallion here from the Rotary Club of Ukraine.
Being in the Museum of Ukraine, visiting my cousins, and I tried to go to Rotary. So I went to Rotary and I did bring a banner back from the Museum back then. That's like 20 years. And now you wouldn't get this. So.
Anyway.
You're involved. Thank you.
Well, you're welcome. So my associates and I are going to go back to the pile and do some more picking, and who knows what we're gonna come up with.
Well, for some of you, probably haven't seen that four-way test banner in a long time. That was taken off the pile too.
Yes. All kinds of, so you brought that in today?
Yep.
That was one of the pile items we picked. All right, more to come.
Stay tuned.
Stay tuned. Thanks. Your payments, take them either in the cups or to Amy.
All right, that is absolutely terrific. And thank you so much for being willing to do that. Yes. So for folks on Zoom who couldn't hear, Marie was looking at the medallion and noticing that the medallion is actually from a part of Ukraine where there's active bombing going on right now. A reminder to be thankful for the health and safety that we have and to wish that for everyone. All right, well, we have another special presentation today, and that is the opportunity to recognize another Paul Harris Fellow. The Paul Harris Fellowship, as you know, is named for the founder of Rotary, Paul Harris, who started Rotary with 3 business associates in Chicago back in 1905. So the fellowship, as we know, was established in 1957 in order to recognize cumulative contributions to the Rotary Foundation of $1,000 or more. And those dollars go on to support a variety of Rotary programs around the world, having to do with everything from maternal child health to, of course, the campaign to eradicate polio, and a variety of educational and humanitarian initiatives. It's through the efforts of Rotarians who contribute to the International Foundation that give life and hope to so many people around the world. And today, it's my extreme pleasure to be able to invite up our own Jake Bacalosi to be recognized as a Paul Harris Fellow. Thank you very much. Please accept your medallion and your certificate as well as your Paul Harris pin.
Thank you, Hogan.
You're very welcome.
Yeah, first thing this morning, Dad wanted to split house. Howard said, Howard, Howard said to me, "The shirt and tie don't match." What could I say after that, right? Thank you all.
All right, thank you, Hayes. All right. So moving along with our club fellowship agenda today, we have, of course, the opportunity to provide some updates and welcomes to our guests. Let's see, do we have any visitors today? Any visitors in the room? Okay, any visitors on Zoom who wish to introduce themselves? All right. Well, hopefully, you'll remember if you'd like to invite any guests to join us at Rotary, that's always a great way to expose more folks in our community, the fun and the fellowship and the good work that we do. I do want to pass along a health and welfare update. I did hear from Jerry Hill today that his wife Diane is in the hospital at McLaren. He said nothing that he's terribly concerned about right now, but did want to share that and to ask if you had any thoughts or prayers that you would send in her direction as a little that very much. Any other health or welfare updates? All right, then we'll go ahead with the 50-50 raffle. So Fred isn't here today. He was feeling a bit under the weather, but our fearless leader, our district governor, is here to ensure that the raffle takes place in fine fashion. Or he's here to swindle us all. I'm not sure. So for third place, number 62904. 62904. All right, Jessica.
There you go. Just get them.
All right, number 82175.
I got it.
82175. All right, John. Terrific.
No. 62899.
62899.
I got it.
All right, so we have to introduce our speaker. So I guess I had a little bit of false advertising. It's not Lynetta Coney who is going to introduce our speaker today. It is Lauren Coney who's going to introduce our speaker today. So come on up, Lauren.
The real deal about Lynetta Coney always works.
Hello, everyone. I just want to start by saying Todd and Patrick are two of the smartest guys I've ever met. So this is going to be a great presentation today.
We'll try not to let you down.
I'm going to read Todd first, then I'll follow with Patrick. Sloan Museum and Longway Planetarium Executive Director Todd Slisher has a 32-year career in managing cultural and museum facilities. Previous to joining the Flint Cultural Center 8 years ago, he spent 13 years with the Detroit Science Center and Michigan Science Center as Chief Operating Officer and Vice President of Science Programming. He also managed museum facilities in Memphis, Tennessee, and Columbia, South Carolina. Mr. Slisher is the co-discoverer of the Hamburg, Michigan meteorite. He has served as principal investigator on NASA and NSF grants. Mr. Slisher serves on multiple boards and steering committees such as the Flint and Genesee Literacy Network, U of M Flint's Citizen Advisory Committee, and he is the current president of the Flint Cultural Center Academy Board. He holds a bachelor's degree in astronomy and physics from the University of Michigan and did his graduate work in public administration at Wayne State University. Patrick Ross has started his position as planetarium manager in October 2021. Prior to joining the Longway Planetarium, Mr. Ross acted as the planetarium and observatory manager and instructor at the Texas A&M Commerce University for 3 years. Mr. Ross completed his bachelor's degree in physics from the University of Michigan Flint and completed his master's in physics and astronomy from the University of Toledo with a focus on studying globular clusters in the help me out,
Globular cluster.
thank you, globular clusters in Triangulum Galaxy. I'm not as smart as these guys. Please help me and welcome me, both of them.
We'll just pass it back and forth. Maybe that's the right way. All right, well, thank you very much for that wonderful welcome. Today I get to do something I don't get to do very often, which is have some fun and go back to my astronomy roots. But I have to tell you, Patrick's the true astronomer. I just dabble a little bit here and there, along with my museum duties. But Lynetta asked us, can you guys talk about something about space? And we're like, sure, we can do that. So we had settled on talking to you a little bit about the Webb Space Telescope that is up there and producing a lot of incredible images. You've probably seen some of them in the news. They are splashy and very beautiful, but we're going to get a little bit deeper into a few of them. So I'm going to kind of start, and we're going to kind of tag team on some of the objects here as we go along. But the Webb Space Telescope, what is it? It's our latest, greatest big space telescope up there, kind of the successor to the very famous Hubble Space Telescope. It wasn't cheap, cost about $10 billion, but it definitely is producing some eye-popping images and some incredible science. Now, just to give you an idea of how this compares to Hubble a little bit, the Webb Space Telescope, you can see there, it's got these mirror segments on its main mirror. They're made of beryllium coated with gold. Yes, actual gold. Maybe that's why it costs so much. But the mirror is actually over 21. Off on. You're gonna give me a seizure up here. But the mirror is actually about 21 feet across, and compared to Hubble's, which is about 8 feet across, it's quite a bit bigger. Hubble's mirror would be about 2 of those segments that you see the mirror up there. It's got a kind of funky shape to it. You notice it's got this kind of weird accordion thing down on the bottom. That's actually a sun shield, which protects it from the heat of the sun as it's orbiting around the sun. That's very important because the Webb telescope sees things in infrared light. And infrared light is a wavelength of light that's just kind of down below the red end of the spectrum that our eyes can see. It's often associated with heat energy. And it's very important to shield the main mirror from the heat of the sun so it can discern things out there in the universe. And speaking of out there, where is the Webb Space Telescope? Unlike the Hubble telescope, which goes around Earth and orbits Earth, the Webb telescope is further out in space, about 1 million miles out away from the Earth at what's called the L2 point, or Lagrange 2 point. There are certain points in the Earth-Sun system that are gravitationally stable. L2 is one of those, kind of further out away from the Earth. So it's very far away, and why that's important is we can't fix it. We can't get there. Astronauts have never been out that far away from the Earth. And so if anything goes wrong with Webb, it's not fixable, unless it's a software glitch. So that was very important, and Webb had a very, very complicated setup. You might remember it was launched back on Christmas Day in 2021. It had to go through about 6 to 8 months of kind of commissioning and unfolding and getting everything together. Luckily, that all worked, and it's now producing some great science. So the Webb telescope, as I mentioned, it's got this big sun shield. So there is a facing away from the sun side and a facing towards the sun side. So the facing away side is very important to keep cold. It's about 390 degrees Fahrenheit below zero. So it's really cold. And to compare that, the hot side of the Webb telescope is about 185 degrees Fahrenheit. So that accordion-like sun shield, what it does is it absorbs all that solar energy and shunts it out away from the actual telescope. And so it keeps that mirror nice and cold. Now, it is an instrument that has a number of different cameras associated with it. There's MIRI, which is a camera that sees in the mid-infrared. There's NIRCam, which is a camera that sees that is in the near infrared. And then there are two what are called spectrometers. I'll get into those later, but what they do is they look at light and they break it into various wavelengths. And with them, they can analyze the chemistry of the things that they're looking at. So that's what they do with the spectrometers on the camera. So that's kind of what, is on the whole package. Now, Webb was built to study a couple of different things. Webb is supposed to study the early universe. This is looking way back in time to the early part of the universe, right after the Big Bang. And so it's looking at the formation of very, very early galaxies. It's also studying galaxy evolution through time, how galaxies change and grow and collide and do all sorts of other fun stuff. It's studying stars and stellar life cycles, from the birth of stars out of clouds of gas and dust, all the way until their death, supernova explosion or planetary nebula or other areas stars die. And it also is looking at exoplanets. These are planets going around other stars. There are now over 5,000 known exoplanets, planets in other solar systems around other stars. And Webb is able, we'll get to that a little bit, but it's able to actually pick out some of the chemistry of these planets. So it's very exciting in terms of what it's being actually able to produce. So with that, I'm going to turn it over to Patrick, and he's going to talk about some of the images, and we're going to tag team from here to talk about images that Webb has produced.
Thank you, Todd. Let's move on to our first image. This was actually one of the first images that was released by NASA for the James Webb Space Telescope back in July. This is looking at an object called SMACS 0723, which we'll all remember tomorrow. This is what we call a supermassive galaxy cluster. And I personally love this image so much from NASA because not only did NASA, with partners of the European Space Agency and other groups around the world, build the most technologically advanced space telescope to date, successfully put it out in the farthest telescope location that's still technically orbiting the Earth, but they also decided to flex with one of the first images. Now, what we're looking at is a supermassive galaxy cluster, and it's a little hard to see in this particular image, but you may be able to see that there's some distortion in the image itself. And this is not an issue with the detector, this is actually intended. And we can see a little bit more clearly, we'll come back to that one, in a similar object. This is not the first supermassive galaxy cluster we've ever seen. Hubble has seen several of them. This one is from a set, the ABLE set, and we can see a little more clearly in this one that we have some of these streaks and these circular lines going around this cluster. Well, in space, there are a lot of strange things that can happen, and one of the strangest came from general relativity that states that massive objects can bend space itself. And in the process, we can have an effect that we call gravitational lensing. You make a very massive object, far more massive than our sun, far more massive than our planet, and you can start to see warping of space itself. And so if you have a galaxy, a star, or some other object in the background, this foreground object, the supermassive galaxy cluster, is actually going to bend light. And so if we go back and take a look a little bit closer at the Webb image, we can see right along here, sort of these streaks. These two objects are the same galaxy. And the light from that galaxy has been bent around the supermassive cluster, so we actually see it twice. Which has another effect as well, because just because we see it in the same or two different spots in the sky, it's going to take slightly different amounts of time for that light to reach our eye. So we're actually not just seeing the same object in two different parts of the sky, we are seeing it in two different times. Now, these are slightly different times. They're not necessarily significant enough in this image to bring new science, but this is the technique we use with these kind of clusters, other clusters and other instruments as well, which is why I say that NASA is flexing with this image. They took their most advanced telescope to date, and then they used space itself as a giant magnifying glass to see even further and more distant than this cluster and the instrument would normally be able to see. If we back up for just a minute, as Todd mentioned, we want to see distant galaxies and old galaxies. As I'm sure many of you are aware, the universe is expanding. It is getting bigger, and we don't really have a great example or understanding of why. But in the process of getting bigger, galaxies and distant objects are what we call redshift. You go into a lab and you study hydrogen or helium, and you take a look at the light it absorbs or produces, it is like a fingerprint. And these distant galaxies you can find that same light, but it's shifted in the spectrum towards red, which is why James Webb is looking in the infrared spectrum. And so we can see to those distant galaxies. And if we take a look once again at our galaxy cluster, doesn't show up the best in this image, but all of these little tiny points we see in the background, these are all galaxies. These are all galaxies that were picked up very easily by Webb, very distant. Some of the ones that are not the oldest we've seen, but are still fairly far in the background, again, are magnified spatially, magnified a little bit easier for us to be able to see and study using instruments like Webb, but also by using space itself to sort of magnify these images. Just once quick look again at our image, and then I will turn it over to Todd.
All right, tag, I'm in. Okay, so this particular image is one of, okay, subjective, I think one of the most beautiful that Webb has produced so far. It's a section of what's called the Carina Nebula. This is a nebula that is visible in southern skies, so we cannot see it in Michigan, but if you go to Australia or South America or someplace like that, it shines very bright in the sky. It's a very beautiful naked eye object. And it's about 7,600 light years away from Earth, quite a ways. If you don't know what a light year is the amount of distance light can travel in a year. It's about 6 trillion miles, so a long way. For some comparison, light goes around the Earth about 7 times in 1 second. So if you kind of project that out for how far it travels a year, 6 trillion miles, a long ways away. The image that you're seeing is about 10 light years across. And this is a large cloud of gas and dust that is out there in our Milky Way galaxy that is forming new stars. Stars form out of clouds of gas and dust like this. What happens is eventually something perturbs the cloud, whether it's a passing supernova shock wave or gravity deformations in the galaxy, and it slowly starts to collapse. And as it collapses, it gets more dense and more dense and more dense, until finally it's dense enough that nuclear fusion can take place and a new star is formed. That's how stars start their lives. And so this image is basically a big stellar nursery, place where new stars are being created all the time. And there are several features that Webb is able to pull out of this image and show you very easily. One thing is this cloud of gas and dust is actually being eroded by the bright ultraviolet light of some very newborn stars in this nebula. And so that's why you can see the area at the top of the image looks more kind of empty with some stars in it and then the gas cloud down below. This is a cavity that those new stars have kind of carved out, and they erode away the gas and dust here. And that's why it's got kind of a weird turbulent shape. This is very similar to like if you went out to Arizona and saw the rocks of Sedona or the Arch or anything else, weathering of rocks, dense areas of gas and dust resist the weathering a little bit more than the thinner parts. And so you get these pillars and columns and other things in the image. And in fact, one of the things you can see is this light blue haze right here. That haze is actually the remnants of gas and dust that has been eroded and blown away from that gas cloud. So you're actually seeing the ionized gas here that's kind of blown away. Also in the image, you see that some of these denser pillars. This is probably an area that right in the middle of a new star is forming, and it's a very dense area of the nebula, so it resists that erosion and sticks out from the top. And then also in the image of the Carina Nebula, all sorts of things going on here. You see these little yellow arcs that are in the image, they're all over it. Those are, okay, those are areas that new stars are born and they're starting to push away through jets, the gas and dust away from them. And we see them as kind of a shock wave in the nebula where they're pushing away the gas and dust. And then one more, oops, going too far here. This is a combined image. That's why it's got a different color. It's the two different cameras working together, but it's actually able to pierce through the gas and dust around the nebula. And so we see little red dots in the image occasionally. Those are actually the cores of new stars forming. So this is what, a little back. Okay, see, I've been talking to the mic, but it doesn't work that way. All right, so so Webb is really a powerful instrument in exploring the stellar nurseries, places where new stars are forming, and it can tell us a lot about how new stars form, the condition they form in, the different chemicals that go in to make up the stars. So really, this is another, kind of powerful tool that we have in our arsenal. The other thing is infrared light pierces dust and gas a little bit better. So unlike Hubble, which can't see through the gas and dust, Webb can actually see the inside of some of these nebulas and give us a little bit better view. So that's Carina Nebula, and next up, Patrick.
Thank you. And one thing I do want to mention about these images, there are so many beautiful images coming out from Webb. You can find them on the internet all over the place. But somewhat the best place to actually take a look at them is actually on your phone. If you have a newer phone, it has a beautiful, vibrant display. And these images are so large in terms of their pixel count. Even in our planetarium, we can't show you it all at once. So you can just sit there and zoom on these images and look at all the fine detail that they have. Next object. This is not one of such beautiful images, at least not at first glance. This object, it's going to have a little bit of science build up, but I think it has a fantastic takeaway. This is the Wolf Riot Star 140. And this was somewhat of a surprising image to see James Webb take. It's still releasing the fantastic images that we're normally seeing, but we're also starting to get into some of the more scientific-based images that are a little more of an interest to researchers than for frontline headlines. Now, what is a Wolf Riot star? Well, if we take a look into the night sky, you can find stars that are called main sequence stars, sort of your general adult stars. And there's different types. We have some that are a little on the reddish side, called M&K stars. We have things like our sun, which is a G star. And then if you go outside tonight, you take a look in the winter sky, face the south, you will see a bunch of brilliant blue, bright stars. These are the A, B, and O stars. Now, something we need to know about the A, B, and O stars is how they actually burn. We're going to go into chemistry class. And I'm sure we're at least somewhat familiar with stars burn through nuclear fusion, right? You have hydrogen in the core of the star, combining with other hydrogen to form deuterium, there's a fun word, that then forms into a isotope of helium, breaks back apart into hydrogen, forms into a stable form of helium, and then the cycle keeps going over and over again. That's probably what you've learned. If you've learned it in a chemistry class or an astronomy class, is hydrogen forming into helium, giving us light and heat and energy. But when we get to bigger stars, there's other types of nuclear fusion. For example, this is a very common one called the CNO cycle, the carbon, nitrogen, and oxygen cycle. We're not going to go into the details of how this works, but the important takeaway is that as these massive stars age, they go from burning hydrogen and helium into burning things like carbon, nitrogen, and oxygen. And as this process goes on, we start to form an iron core, which is very stable, but you can see there's several other elements, silicon, oxygen, neon, carbon, helium, hydrogen, that starts to get displaced and built out to different parts of the star. Now, each time it sort of kicks up to a new version of nuclear fusion, there is more energy being output. In the same way we saw in the Carina Nebula, that bright light can erode the nebula itself and push that dust and gas away. As these stars start to build up, it actually produces enough light to shed the hydrogen and helium that's at the edge of the star. So a Wolf Riot star is where instead of having our regular O star, where it's nice and happy and burning its fuel, the outer edges are starting to get very wispy and burning off into space. And that is still not enough to explain what this image is. In fact, compared to the Carina Nebula, it kind of looks dirty. It's like someone's got a fingerprint on our lens. Well, this is where the magic comes in. This star, Wolf Riot 140, is not a single star. It is what we call a binary star. There are two stars out in space, and they are orbiting each other around a common center of mass. So the same way we can have the Earth orbit the sun, we can have two suns out in space orbiting around each other. And every time these two stars, for example, we have one right behind him, we have one down here, and you will see there are spots where they get very close together, and there are parts where they're very far away. When these two stars get close together, the gravity from the companion star takes that solar wind and flings it off into space. And that is what we are seeing in this image. But this is cyclical, and this is measurable. These stars, these binary stars, have an orbit around each other of 8 years. So every 8 years, like clockwork, it is going to send off a ring of dust out into space. So when we look at this image and we see these rings, this is the same concept of being able to cut into a tree and count the rings on a tree. Every time we see one of these rings, it is an 8-year cycle. Now, I again recommend look at this on your phone, a little bit dim in our projector, but as the rings go out, they do get dimmer because you're taking that dust and gas further away from the star and it's cooling down. It's not able to emit the same amount of light. So we do have an end time, right? We can't go back to the beginning of time and count how many rings there are, but it's the exact same process or the exact same idea as counting the rings on the tree. And so with no other information, we can start to deduce a lot of the physics of what is going on with these stars just through very simple analogy.
All right, so a couple more items here. Then now we get into the exoplanets and what Webb has been doing looking at the planet. This is WASP 96b. The star is named WASP 96. The B refers to a planet that's orbiting it. This is a very large, hot planet. It's like Jupiter. It's a gas giant planet out there, and it's going around a star about a little over 1,000 light years away. Now, this planet is very close to the star. It goes around in about 3 days, so it's very, very hot. Now, Webb didn't discover this planet. It was actually discovered in 2014, but Webb can do something very specific with these planets that we've never been able to do before. So first of all, how do we find these things? You know, planets are pretty tiny things compared to stars. And how do we find them? Well, we don't actually look at the planet themselves. We actually look for 2 ways that we can find them. One is the big planet, it'll actually cause the star to wobble, to move a little bit. And we can see that motion either back and forth or towards us and away from us. That's one way to detect it. Another way to detect the planet is if it happens to cross right in front of the star in something called a transit, it will actually dim the light of the star just a little bit. And we can pick that up. And that's how we've been finding all these exoplanets. So in these transiting planets, and here you can see on that graph below, that's the normal level of starlight. When the planet passes in front, it dims down, comes back after the planet moves out in front of it. But Webb can take advantage of this. And that what it can do is it can look at the light that travels through the planet's atmosphere on its way to us and use those spectrographs I talked about before to determine the composition of the atmosphere. We can actually tell what's in the air of these planets using Webb. And so WASP 96b was the first one that we tried this with. Now, it turns out one thing that we found about this gas giant planet, got a lot of water vapor in the clouds. There are probably water clouds around this planet or mist or something along those lines. So this is one of the first detections of water outside our own solar system in another solar system. That's very important because when we find water in our solar system, we find life. And who knows, maybe we'll find some traces out there. Now, this particular planet is not the only one that Webb has looked at. It was just the first one. We're now starting to look at other planets. We've done a couple other gas giants, and one that's really, really interesting is a planetary system called TRAPPIST. This is a system where there are more rocky planets like Earth, about Earth size, not Jupiter size, not Saturn size. These are down the size of Earth. There are 7 of them going around a very cool star. And Webb has just started to look at the TRAPPIST planets and look at their atmospheres. And so you're going to hear some amazing science coming out probably in the next 6 months with things that Webb is finding out about TRAPPIST. This literally came out about a week ago, the first observations of the TRAPPIST system, but they've been doing many more. So they'll explore this. And one of the things exciting about the TRAPPIST system is 4 of these planets are actually in the star's habitable zone. That means that they are in an area where liquid water can exist. So we're really drilling down now with the Webb telescope and looking at planets and their composition and what they're made of and what their atmospheres are like. And eventually we'll be able to look at things like oxygen, carbon dioxide, other elements that are in the atmospheres and tell whether they're Earth-like or whether they're different. So this gives us a capability that we've never seen before in a space telescope and is something that's really exciting about Webb. All right, last object.
Yeah. Could we get total darkness for this one? This one has a lot of very small but bright objects. So we're going to see if we can't get a better view of it. But as we get the lights turned down, I do want to set the stage for this object. This is, oh, that's so much better. All the way. Perfect. Absolutely perfect.
We're used to working in the dark.
This is the JADE survey. This was taken by the James Webb Space Telescope, obviously, and it is a deep field survey. What in the world does that mean? Well, for one, it's not the first deep field survey. In fact, this is the Hubble Ultra Deep Field. This is probably the more famous one. It's been around for several, I think, decades at this point. I think it was in 2004, 2006 that this image was taken. But to set the stage for this, of why this is so important, Hubble, the scientist, which we named, of course, the Hubble Space Telescope after, was the one to discover that the universe is expanding. And he was using Mount Wilson, a telescope out on the west side, to be able to make these observations. This was around the early 1900, 1914, I believe was about that time. 1900, very late 19th century, there was a great debate, right? We took a look at objects in the night sky. We see things like the Andromeda Galaxy. We see things like nebulae. And there was a debate. Are we seeing objects that are outside of our galaxy? Or are they just very distant, but still part of our galaxy? It was this existential question of, is our galaxy synonymous with the universe? And Hubble was one of the people, they sort of ended the debate in the 1900s, but when Hubble looked at his observations, it was brand new in everyone's mind that there are even different galaxies out there. So after the Hubble Space Telescope was launched, some scientists had a brilliant idea to point the Hubble Space Telescope at a small patch of the sky that has very few stars in it. It was basically empty. And then it took a long exposure. So the same way, even with our cell phones nowadays, you take long exposures to see objects in dim light. This is what Hubble did. And every single dot that you see here is a galaxy. Every single one. It took hundreds of hours of exposure time to create this image. And as we alluded to in the beginning of the talk, these galaxies, because they're redshifted, because the universe is expanding, these galaxies are very far away from us. And because the speed of light is constant, that also means the further away you get, the further we look back in time. So these are also very young galaxies. And if we were to take the Hubble Ultra Deep Field and we were to slice it, we can actually see that some of the galaxies in the foreground, they're about 5 billion years old. Other galaxies in this image are 5 to 9 billions of years old. And then you can keep going back in time even further. Now, of course, Hubble had a limit of what it could see, because as you go back in time, you get more and more into the infrared, which is why we need James Webb. So this deep field, we'll zoom in a little bit, is basically looking in the same region as the ultra deep field, and it's trying to find even more galaxies and even more distant galaxies. We zoom in a little bit, we can see a little more detail. It's always fun to look at the nice large galaxies that we can see some of the structure to, but I really want to stress that these tiny points of light that we are seeing as we get closer and closer, this is a whole galaxy, a galaxy home to billions of stars from the very early stages of the universe. Now, this image is also somewhat controversial, not in the sense that there's anything wrong with it, but it is stirring up some news in the astronomy field. Not in the way we see it from the news standpoint, but from actual astronomers. They have taken great interest in this image. Because if we draw a map or we draw a timeline of how the universe was supposed to be formed, we have a bunch of physics, a bunch of cosmology, a bunch of models that tell us this is when we get our first stars, this is when we get our first galaxies. And if we take a look at our JADE survey, these tiny dots of light that we see in here, some of them are so old, they don't agree with our model. So there is something with our model that we don't understand. Now, there's a few innocent examples. For example, our Milky Way galaxy is full of dust, and it can obscure how much light we see, and that gets factored into the model. So maybe the early galaxies don't have a lot of dust. Maybe they just shine brighter than the galaxies that we're able to see closer to us. But then there's also ideas that, well, maybe our understanding of cosmology isn't quite where it needs to be. Which again, was one of the points of the James Webb Space Telescope, was to find places where our models don't work. If we thought our models of the universe were perfect, we would just, clap our hands and call it a day. We wouldn't need to build new telescopes. So we're really, oh, one too many, really excited about this image. The likelihood that it can completely overturn cosmology is next to nothing, but there is going to be new science coming out of this, new understanding of cosmology, new understanding of how our universe is formed, and new ways to use Webb to be able to create some images like this that can give us new understandings as well. That is the last image we have to talk to you about, so if we can get some likes back, that'd be greatly appreciated. And I believe we have a few minutes for questions. Yeah.
Billion, a billion.
Carl,
It's a good number.
Yeah.
You back up. Had, three, yeah, like.
Yes. Yeah.
My question is, how can you tell, what's the, galaxies that are 5 billion years versus the ones that are further out? Because clearly it's size.
That is an excellent question. How do we actually measure how far away these galaxies are? We'll go all the way back. Same idea right here. So as these galaxies are out in space, they are moving further away from us. They are in fact accelerating away from us due to the inflation of the universe. And when we look at the spectra, so when we look at the image, we can't tell. When we look at the spectra, which isn't as fun, so we don't show it, we are able to see shifting in where we're expecting to find either emission lines, light that we can see, or absorption lines, where light's getting absorbed by the galaxy. And there's very specific wavelengths these things are supposed to exist at. And when we measure these very distant galaxies, we are able to see that they have moved. And how much they've moved gets correlated to how far away they are. Now, one really cool thing about astronomy, we call this redshift, and we use it to denote it with Z for whatever reason. So if you look at the redshift or the Z value of these galaxies, if you look at one that's 1 billion years away from us, and then you look at one that's about 2 billion years away from us, it's about a linear progression, right? It looks like a line. But as you get further and further back in time, it starts to curve off, which means it's actually really difficult to pinpoint just how old these ancient galaxies are. Because one of the reasons why the JADE survey is causing a stir is also, well, how much of that is just error in our model? How much of that is a limit to our understanding and our measurement, right? There's a lot of questions to be answered. So thank you for that question. Yeah.
I'm sure who, couple ones, who came to
Okay. So James Webb, he was the director who oversaw the Apollo program. So we've basically recognized, by naming the telescope after him, we've recognized the contribution that he made to the Apollo programs, to the space race, to NASA itself. And something to keep in mind, I have to tell the little ones when they come to the planetarium, they have such a different view of the space race than people who went through it. We weren't winning the space race in the beginning. We were behind with the Mercury program. We were behind with the Gemini program. We only pulled ahead of the Russians during the Apollo program, which is another reason why Webb is so celebrated, is it was a fundamental shift in where the US stood compared to the other powers in the space race. Yeah. Yeah.
When Tom said where the thing.
Mhm. Yeah. Yeah, that is an excellent question. It's the best way that I can explain is it's weird quirks in math. And if you don't believe me, what I recommend you do is when you get home, Google the Trojan asteroids. There are, if we pretend, instead of looking at Earth, let's pretend this is Jupiter, right? Just like with Earth, it's going to have 5 Lagrange points. We only talked really about L2. But same way we have this fictitious point of, not fictitious, it's real, but this quirky gravity point out past the Earth. We can also see we have one just ahead of Earth's orbit and one just behind. And if you look at the Trojan asteroids, these are asteroids stuck in Jupiter's orbit, and they live at L4 and at L5. So it's a very strange thing. Going through a master's program, I've done all the math for this, and it still seems like magic. So maybe the better idea is go find some proof and go look at the Trojan asteroids, and you'll be able to see that very clear pattern that it pops up, and you're like, oh, this is a real thing. It's not just on a chalkboard.
talk about finding it? And what is the-
So it's both of the stars' mass. Basically, it's an average, right? You take the position of the one star, you take the position of the other star, and the math is, and the way the math works out is sort of this average point in between that they'll orbit around.
Now, it's
Correct.
called the common center of mass. It's basically, if you take the two masses, add them up on a straight line between the two, the common center of mass will be somewhere on that line, and it'll be closer to the heavier star than the lighter star, but that's the point that they both orbit around.
Makes you wonder how that-
Oh, yes, come to the planetarium, ask me that question. I have so many visuals to show that. I taught a bunch of fifth graders that today. So, and they said it was better than the Detroit Zoo, so. There you go. Any other questions? Yes.
I'm a little, confused. I'm looking at L2.
Mhm.
Is that following always behind Earth while Earth is orbiting?
Correct.
So the telescope's always following Earth, it's would go way faster than Earth.
Yes. So the question was, if we take a look at L2, how is that going to compare to the relative position of Earth as it orbits around the sun? And you can imagine drawing a line like we have right here. And as you rotate the Earth, it goes around the orbit, you rotate this line, and L2 will always follow behind Earth. So the Earth will always be between L2 and the sun. And so, yes, it is actually moving in its orbital speed faster than Earth is in order to keep up with it. Yeah. Yeah, I will turn this one over to Todd. Give him a chance.
So I think the question, talk about the slides of our galaxy, or the size of our galaxy. Okay, well, our galaxy is kind of a typical spiral galaxy, about 400 billion stars or so in terms of the absolute, number of stars in it. There are other bigger galaxies. Andromeda is slightly larger than ours. There are other smaller galaxies. There are two dwarf galaxies that actually circle around our Milky Way. But we're kind of in a typical spiral galaxy, if you call that. What is it, about 100,000 light years across? Is that right, Patrick? I think it's about 100,000 light years across if it's like a record disk and you measure all the way across the disk of our galaxy. All right, I think we're about wrapped up. So thank you very much.
So I found that fascinating. I love astronomy. I appreciate you making me feel like I understood a little bit more about the universe today. And on top of that, I think if I won't probably ever start a rock band, but if I do, it's now going to be called Wolf Riot. So thank you very much. In honor of your talk here today, we will be making a contribution in your name to Rotary International to help aid in the elimination of polio. So thank you so much.
Thank you.
And for those of us who are wanting to ask more questions and continue on this, maybe we'll have to include a link to upcoming long-wave planetarium programs as one of our upcoming weekly messages. And I think somebody had even put out the idea of weekly or a monthly trivia night.
We used to. We have discontinued the trivia nights. We might bring them back occasionally, but we have some other stuff.
Well, if you do, we might have some trivia buffs who are game.
We do web updates regularly. We have what's called our First Friday lecture series, where we talk about various topics in astronomy. And so the last First Friday lecture series, so this is kind of a spin-off of that Patrick did on the web space telescope. So,
Right. Well, we'll include some links to that kind of information so that the folks want to continue learning, we have opportunities to do that. I want to thank everybody who helped to put together today's meeting. Not Lynetta, but Lauren Coley for introducing our speaker, Julianne Krasinski for giving our inspirational message. Thank you to Howard Downey for taking notes, Mike for your help with setup and takedown, as well as the assistance with the raffle. And thank you everybody for being here. Please join us again next week where we will be hearing from one of our very own, Raphael Turner from Consumers Energy will be speaking to us about their various clean energy plans, and so we have an opportunity to hear from them. And I hope that you will join us for that. So with that, thank you, go forward, Imagine Rotary, and we are adjourned.
Everyone.